everyone. Welcome to today's Near Boiler Piping webinar, a 1-hour, 1 PDH credited presentation. My name is Miranda Getling, and I'm the Viessmann Academy Manager. I just wanted to take this opportunity to say thank you for attending today. We appreciate you taking the time to attend this webinar, and I hope that you are all having a great Tuesday so far. Today, your webinar instructor will be Jody Samuel. Jody is a graduate of Maine Maritime Academy with a degree in marine engineering. Over the past 20 plus years, he has worked with various companies, including Amtrol, Viessmann, and Calefi, serving in various roles, including application engineer, product manager, training manager, and manager for engineering education. Currently, he serves as the project development manager for Viessmann. Before we begin, just a few housekeeping items. As stated, this is a 1 PDH credited presentation, and we do this through RCEP. And the RCEP does have a required survey that must be filled out if you would like this PDH credit. So we will be sending that survey out to you by the end of the day today. So if you do need that PDH credit, please do fill that survey out. If you don't need the credit, you will still receive the survey. We ask that you please take the time to fill it out to help us further improve our webinars. If you don't remember if you indicated on the registration form if you needed the PDH credit, my email will be on the last slide of this webinar. Feel free to email me to double check on that. And then once you fill out the survey and we submit you for the PDH, the certificates will be emailed out within about 5 business days. If you would like a hard copy, please let me know and I'll make sure to do that as soon as possible for you. Everyone will stay muted throughout the webinar. However, at the bottom of your screen, you should see a Q&A button. You can submit any questions throughout the entire webinar through this section. Jody will be stopping about halfway through and at the end to answer any questions submitted. We will be recording this webinar, and in about 2 weeks or so, it will be posted on the video library, which is located on the same website you went to register for this webinar, the Viessmann Academy website. There are 2 spots where you can go to view the video library. The first is in the header of the web page, or if you scroll down, there is a video library section that you can simply click into. Once you are in that video library, this is what it will look like. And we have added in a search option up top, so you can simply type in near boiler piping. And if it is uploaded by that time, you will have that video pop up for you. We also have a drop down of different sections. And this particular webinar will be in the recorded webinars section down below. So with that being said, let's begin. Here is Jody Samuel.
Thank you, Miranda. So today's presentation is on near boiler piping. Good to be with all of you. And for me, this is something that from the presentation standpoint, it's based on, a lot of this is on conversations that I have with people on a regular basis. As Miranda said, my position is project development manager, and part of this also becomes application engineering. And so I have a lot of questions about application engineering that deals with near boiler piping. And so a lot of this is based on the questions that have come through on that side of things. So before we get moving, a couple of housekeeping slides. Miranda already talked about RCEP, so we'll skip through that one there. The presentation, if you desire a copy of it, it is available. We can get it to you as a PDF. Just when you're taking the survey, just put a note in there to Miranda about getting the presentation. I'm going to skip through the purpose and jump into the learning objective. So this is what we're really going to talk about today. So we're going to, at the end of it, you should be able to describe the purpose of the components required to complete a boiler installation for the near boiler components. Describe the best location for the near boiler piping components. Explain the methods of isolating off-cycle boilers. And explain the differences between primary only. You'll also hear this referred to as variable primary and primary secondary pumping. Now, when we look at that last one, we're actually going to start on the bottom and work our way to the top. But that's one that probably comes up on a common basis when we talk about various boilers. Yeah, and for me, when the calls come in, you know, I deal with a lot of people looking for, from the application side of things, for instance, piping diagrams. The calls come in. So, and the piping diagram calls come in a wide variety of format. Sometimes the calls or emails or texts come in with a full detail of what they're looking for. But a lot of times on a regular basis, I get the call coming in or the email. I need a piping diagram for 2 fill in the blank boilers. and that's about all the information I get. So based on the boiler that they're throwing at me, then becomes the questions. And always for a lot of these, the question really is, do you want primary only, variable primary system, or are you looking for primary secondary? And a lot of times the response I get back is usually one of three. Let me check with the engineer and see what he wants to have for the arrangement of the boilers. The other one that comes in a lot is, well, you choose. Decide which way you think it ought to go and give me a piping diagram for it. Or sometimes the third one is, well, I'm not sure. Can you send me 2 piping diagrams, one of each? So we're really going to look at this, because a lot of times the question really comes up is, when we look at doing this, is it really the decision for doing primary, secondary, is it based on the boiler, or is it based on the designer preferences? And so that's kind of where we'll start our discussion about this. And what you'll find from an aspect of piping, near boiler piping, it's a little bit of both. Yeah. Sometimes, depending on the equipment, it is based on the boiler designs, but sometimes it's going to really be based on preferences. So when we start this conversation, let's talk about a couple of boilers. Okay. So when we look at boiler choices, the boiler choices really come down to 2 styles of boilers. We'll call them water tube boilers and fire tube boilers, okay? And each one represents different design criteria that bring together a different package, if you will. So let's start with the wall-hung boiler. So wall-hung boiler, in most cases, are going to be water tube, particularly when we start to get into the commercial sizes. And from an aspect of what I do, I tend to deal more on the commercial side of things than on the residential. So a wall-hung water tube boiler. Okay, and as a wall-hung boiler, one of the key design words are compact. It has to be compact. So this boiler here at 530,000 BTU input, it's 298 pounds of boiler. Size-wise, it's 27 by 24 and 44.5 inches tall. It has a heat exchanger surface area of 36.78 square feet. It's low mass. It holds 4 gallons of water. The maximum flow rate is 38 gallons a minute, and at 38 gallons per minute, it's about 16 feet of pressure drop across the boiler. So when we start to look at that boiler, that's what that represents based on the design criteria. It has to be compact, and you should be able to hang it on the wall. Now, the other boilers are floor standing boiler. Okay, so this floor standing boiler is of a fire tube design. It's a very unique fire tube, but when it really gets boiled down to, it's a fire tube boiler. Okay, compact is not part of the design criteria. This boiler weighs 503 pounds, and its footprint is 73 inches by 36.5 inches, and it's 66 inches tall. It's 663,000 BTUs. Why I chose that size is, if I look at the wall-hung boiler, that's the largest of the wall-hungs. This is the smallest of the floor standing in that commercial line. So they're sequential in the size of the boiler. So that's why I chose them for this discussion, okay? So for this floor standing boiler, the heat exchanger surface area is 72.9 square feet. It's high mass. It has 81 gallons of water inside the boiler. Its max flow rate is 176 gallons per minute, and its pressure drop at 63 gallons a minute is 5 inches of water column. So really a lot different style of boiler, but again, both these boilers are condensing boilers, so they're trying to achieve the same thing. Now, when we look at the application of these boilers from a near boiler standpoint, there's a few things we need to look at, and this discussion kind of works it out of whether a boiler should be utilized as a primary, secondary install, or possibly is this a better boiler to go with a direct connect, a variable primary installation. So let's start off with the wall-hung boiler. Okay, well, gonna back up here. And from our discussions, we're really focusing on 3 items, okay? The output of the boiler, the heat exchanger surface area, and also the mass of the boiler, because that tells a lot about how that boiler has to be applied. So for this wall-hung boiler, okay, and I'm going to concentrate on two items, two characteristics of the boiler in this discussion. So here we're looking at the gallons of water and the output of the boiler. What we're really trying to look at here is what is the, how many thousands of BTUs per gallon of water inside that boiler do we have? So if I take the 495,000 BTUs and I divide that by 4 gallons, that tells me that in this boiler, I have 123,750 BTUs per gallon of water, okay? Now, if you look at that number, we start to compare it to the floor standing boiler. A little note about this number is this amount of BTUs per gallon within the boiler, that's fairly consistent for what you see for a well-hung water tube boiler, okay? But really, that's the amount of energy based on the amount of gallons in the boiler itself, okay? Now, if I look at the floor standing boiler, it has 81 gallons of water and its output is 643,000 BTUs. I do my math, I'm at 7,900 BTUs per gallon of water. Significantly lower ratio of water to firing rate of the boiler. Okay, so what does this really mean to me and why am I bringing this up? Okay, now when we look at a comparison between the two, okay, this boiler here, I divide the 124,000 by 8,000, I get a ratio where this boiler here has about 15.5 times the output per gallon of water in the boiler compared to this boiler here. Why is that significant? It's really significant when we start to look at the boiler and we have a mismatch between the firing rate of the boiler and the load of the system. Mainly, I'm firing the boiler at a higher firing rate than the load of the system, okay? And with this boiler here, because of the fact that I have a lot less firing rate input versus the number of gallons, the volume of this boiler allows the mass of the boiler to moderate the temperature change. What it really means is if there's a mismatch, this boiler responds, its temperature changes much quicker than this boiler over here. It's a much moderate change when there's a mismatch between the two until the control circuit catches up with it. So we start to look at system design. That's something we have to consider when we look at the two styles of the boilers. Now, the next thing we want to look at is the heat flux. How many BTUs of energy am I putting through every square foot of heat exchanger? So with the wall-hung boiler here, the water tube boiler, again, I have 495,000 BTU output. My heat exchanger surface is 36.78 square feet. If I calculate the heat flux, I come up with 13.46 or 13,460 BTUs per square foot. Again, as a reminder, this boiler is designed to be compact. The heat exchanger and everything have to fit within the cabinet. Now, if I go to the floor standing boiler, with that floor standing boiler, I have 643,000 BTU output. The heat exchanger is about 73 square feet. If I do the math, I get 8,820 BTUs per square foot. Okay, less BTUs or much lower heat flux compared to the wall-hung boiler. Now, if I look at this from a ratio standpoint, if I ratio these two, so I take my 13.46 over here versus my 8.82, I get 1.53, which is telling me that the heat flux within this boiler is 53% higher than the heat flux over in this boiler here. So if I look at that surface of the heat exchanger per square foot, I have 53% more energy that I have to move off the face of that heat exchanger, okay? So when I start to look at the water tube wall-hung boiler, because of this higher heat flux, it's much more critical to keep water flow across that heat exchanger. Remember, this is only a 4-gallon boiler. That water flow across that heat exchanger to pull the heat off of that heat exchanger face to allow the boiler to operate properly. So again, this becomes another concern or another point of discussion when we start to talk about whether I'm going variable primary or I'm going primary secondary. Okay. Now, the other thing that we have to consider is how are we controlling the boiler, okay? So when we look at boiler control, I look at modulating of the burner because the burner is where I'm going to balance the input to the load of the building. I'm going to change the firing rate of that burner. Now that burner's modulation is going to be based on outlet water temperature, okay? Now, the thing with heat loss within a building does not rapidly change load. If I look at a building, the outside temperature doesn't all of a sudden in 15 minutes go from 45 degrees Fahrenheit down to 15 degrees Fahrenheit. That happens over long periods of time, okay? So you have a load that tends to change slowly. So we don't have to have a boiler control that's set up for rapid response, okay? We actually want to have it for a slower response. The plus side of that, it reduces the amount of hunting that happens. It hunts less, and when I look at adjustments, the burner can run for a long period of time without making adjustments. So we're really looking for a slower response. Okay. Now, when we look at that operation of that burner and making the decision on when to change the firing rate or modulate, it's all about the feedback from the control circuit. Okay. And in this feedback for the control circuit, one of the things that is one of the factors that are involved is what's called an integral. Okay. So an integral is one of the key pieces of essentially the arrow loop for the feedback circuit. Now, when we look at this integral, it's a time temperature based value. The way to think about it a lot of times when we do this is right down here, accumulated error, okay? Now, the best way to think about accumulated error is this chart down here, this graph showing a curve on an XY axis. So if I look at this and I'm thinking about integral, this axis here, let's call that time. This axis here is temperature. And what we're doing with this integral is we're measuring the area under the curve. You know, it's the kind of things that us engineers loved back probably sophomore year in college when you had to go through calculus and other math courses to become an engineer. But that's what we're really doing here with this integral. It's really about the accumulated error, or really the area under the curve. And so from a boiler standpoint, it's about I accumulate the error, and when the error becomes great enough, then there's now time to make an adjustment on the burner. In our control logic, you'll see it listed in the coding as integral threshold value. And our default value is 30 K minutes, and the K is for Kelvin minutes. Kelvin minutes, temperature, and time. So when we start to look at this and we look at the operation of the boiler, this is what we're dealing with from a control standpoint. Okay. Now, everything is well and good when things happen slowly. We're able to measure the temperature, allow the time to accumulate, and then make the adjustments, and the boiler modulates, and there's not a lot of cycling, and nothing touches the limits. Things operate a little bit differently when we start to change the load quickly. So for instance, if I had a system where my system design temperature was a 20-degree delta T, through this formula in here, it's our BTU formula. We'll come back and reference this. It shows up in a lot of different presentations. But let's say I have a system and I have a sudden change in flow rate from 100% down to 20% very quickly. Okay. In a hydronic system, how does this happen? The ones that I've have had discussions with people over, a lot of times centralized around doing night setback, where all of a sudden, say at 5:30 at night, they reset the temperature, the ambient temperature in the building down 10 degrees, say from 70 to 60 degrees. And at that very moment, 80% of the control valves go closed in the building. All of a sudden, the flow rate drops from 100% down to 20% or even lower, okay? And what happens is when I drop that flow rate, initially, the BTUs per hour are not going to change, okay? What's going to change is the flow rate. So if I drop the flow rate, since the flow rate plus the delta times the delta T has to add up to the same BTU input, for whatever percentage I change the flow rate, the delta T has to change in the opposite direction, the equal amount. So if the flow rate drops by a factor of 5, the delta T has to increase by a factor of 5. So what'll happen is if I started off at 20-degree delta T, control valves go closed, I'm down to 20% flow, all of a sudden the boiler starts, the water temperature in the system starts to drive itself up towards 100-degree delta T, okay? And this happens very quickly, okay? Again, when we start to look at operation, when this kind of event happens, depending on how quickly the system can respond to the change. The system may respond and be able to operate through modulation, or what may happen is it may be quicker than the integral, and all of a sudden the boiler has to start cycling to bring everything back into control again. Okay, so we have criteria within the controlling of the boiler. There's heat flux. There's also the BTU per gallon ratio, if you will. So how does this all play into the piping of the boiler? Okay, so if I look at a compact wall-mounted boiler and I compare it to a floor-mounted boiler, it has over 15 times higher BTU per water content. Okay, so there's less mass to moderate the increase in temperature when there is a change. Additionally, it also has 53% higher heat flux. So there's more of a need to maintain a constant flow across that heat exchanger to pull the heat away from the surface of the heat exchanger. You take this and you couple it with the typical flow response rate a boiler control has, you end up with a boiler that's more sensitive to changes in flow rates because of all of this. Okay, so what it really boils down to is when we start to look at making the decision between primary, secondary, or primary only or variable primary, if you will. If I look at wall-hung boilers, because of the flow requirements of a typical wall-mounted boiler, a low-mass boiler, for all the reasons discussed, the primary, secondary piping is recommended. So I do a small-mass wall-hung boiler, it's going in primary, secondary. However, for fire tube boilers, because they have that higher mass, they have lower heat flux, and then the mass allows everything to work with each other, even though the control is responding at a slower rate. When I do a higher mass boiler, I don't necessarily have to do primary, secondary. I can do variable primary as well. So really, with this boiler here, with this style of boiler, this really becomes the designing engineer's call on which way to go in. Do I want to go primary, secondary? Do I want to go variable primary? Okay. So what you end up with, but when we start to do this, all of a sudden, particularly when I'm in areas where the comparison or the alternative options could be doing, I could do either wall hung boilers or floor standing boilers. There are other items that make the wall hung boiler much more attractive. Okay, so with the wall hung boilers, because it is compact, there's a lot of things that we look at and say, you know what, these make great sense to use instead of doing the floor standing boilers. First off, these wall hung boilers are very portable. So they're easy to get in and out of the mechanical room. So I don't have to worry about doors. When I look at stairwells, I don't have to worry if there's a 90-degree turn halfway down where I can't get a larger floor standing boiler. The other big advantage of going with the smaller boiler, the wall hung boiler, is about system turn down. Typically when I start to look at the wall hung boilers, because I'm stopping at 5 million, I'm probably gonna have 2, 3, or 4 to meet the load of the system. So now I have system turn down working in my favor. The other thing with the wall hung boilers is I typically end up with reduced redundancy needed. Even though the requirement's probably going to be n+1 on redundancy, I do a building where the load of the building is 1 million BTUs. I do a 1 million BTU floor standing boiler. All of a sudden, my redundancy becomes another 1 million BTU boiler. If I'm doing the wall hungs at 500,000, the redundancy becomes 500,000, 500,000 BTUs. So now I'm at 1.5 million, versus the 2 million. And at that point, by the way, the footprint's also smaller. Okay, I can separate the flow rates and the delta T's. So all of a sudden, my system flow rate and my boiler flow rate don't have to match. The other big advantage that going with this style of boiler is there are manifold systems available that simplify the installation, even though I'm maybe doing an extra boiler or two by going to the wall hung boiler. So although this boiler is tied to specifically doing primary, secondary, there are other things that also make it very attractive, when I look at doing this versus possibly doing a different boiler in a variable primary install. Okay, so if we look at our different piping arrangements that are available, so we talked about the higher mass boilers doing variable primary. So here's variable primary. So system connection is here, directly into the boilers and back out. So it's all within the same loop. The pump that's moving water through the heat emitters is moving the water through the boiler as well. Okay, this one shows it with isolation valves. And then there's also installations out there sometimes we'll see without the isolation valves. And we'll talk about that further on down. Okay, now the other option is going with primary secondary. Primary secondary, I can go with either style of boilers, the wall hung water tube boiler or the floor standing fire tube boiler. Okay, so primary secondary, it's really all about this. Okay, so I'm going to have some sort of connection, some primary secondary connection. It can be closely spaced tees. The closely spaced tees should be at a maximum of 4 pipe diameters apart. I want to reduce the pressure drop in this crossover piece here. This way here, I've hydraulically isolated the boiler loop from the system loop. So the boiler loop can have a flow rate based on what's required for the boiler. The system can have a flow rate that's required for the system, and neither operation affects the other operation. So this is primary secondary as executed as closely spaced tees. Okay. Also, I can do primary secondary with floor standing boilers. So you have the same thing here. Here are my closely spaced tees. There again is my max 4 pipe diameters. And it gives me that, again, the ability to bring the boilers outside of the system loop, put them in their own boiler loop, and allows me to design specifically for what I would like to see for a delta T across T air, regardless of what I'm going to see for a delta T across the system. Okay. The other thing it does is from a pipe pumping standpoint, the system pump doesn't have to be sized to flow water through the system and the boiler. This pump is sized for what's needed for the heating loop. These pumps are sized for what's required for each individual boiler. So there are advantages when I start to go with the primary secondary versus the variable primary. Okay. Now, when I do primary secondary, one of the piping options that are available is what's called a low loss header. Okay. So the low loss header really is a pre-engineered hydraulic separator. So I put this in the system. I don't worry about the 4 pipe diameters of spacing. The design of the low loss header gives me that hydraulic separation. Okay. And the other thing is with this hydraulic separation, there's a couple other advantages that it brings to the table. Now, we're saying low loss header. You may have heard the low loss headers also referred to as hydraulic separators, hydraulic decouplers, or even hydraulic bridges. They're all the same thing. Now, how they work is internally, the internal area within the hydraulic separator is much larger than the incoming piping connections. And in sizing, the body of the hydraulic separator is designed for a flow rate of about 0.7 feet per second velocity inside there. At 0.7 feet per second, inside the body, there's virtually no pressure drop whatsoever. So that's how we get this hydraulic separation, so that what happens on the system side does not affect what's happening on the boiler side. And then what will happen is through the body of the low loss header, you'll see water movement to balance any unequal flow on either side of this low loss header. Now, a couple of things. We talked about some other features that this does pick up. Okay, coming in here, typically your flow rate is probably going to be in the neighborhood of probably about 4 feet per second, could be even higher. At that speed, if there's any air that comes out of solution in the boiler, it's going to be entrained along. So when I get to that low loss header, all of a sudden I drop the velocity down considerably. When that velocity drops, I lose the ability to entrain the majority of the air, and it does release in here and tends to catch in the top. So it can be an effective air separator. Okay. Same thing happens on the return side. If there's any dirt or debris in the system, the velocity of the water tends to move that dirt along until it hits a point of low velocity. Again, inside the low loss header is a point of low velocity. So you do end up with a fairly effective dirt trap on the bottom as well. So although it's there for hydraulic separation, there's a couple of features that are also picked up as auxiliary or ancillary features in the low loss header as well. So from an application standpoint, the low loss header replaces the closely spaced tees. So here's the boiler out here. Here's my low loss header. Here's my system supply out here. The boiler is hydraulically separated from the system, so I can pump that boiler at the rate that's required for the boiler. And the system over here can either run at a fixed rate or run variable based on the needs of the building. Okay. As we said earlier, hydraulic separation, primary, secondary, is required with the wall-hung boilers. So here's a rack of 3 boilers. Here's my hydraulic separator, my low loss header, and then here's my connection out into the system. This can be done by individual boilers, individually mounted. Oh, we talked about a manifold system. So here it's shown on the manifold system as well. But manifold system, low loss header, and then out to the building, okay? But when we start to do primary, secondary, you notice this primary, secondary pretty much is applicable to every boiler out there. It's just a matter of, how you want to achieve it. And then when we start to look at the variable primary, the primary only, now we're typically looking at fire tube boilers, your floor standing larger mass boilers. Again, in summary, primary, secondary is required or recommended when I do wall hung boilers, low mass water tube boilers. But when I do floor standing fire tube boilers, typically there's a large mass in there, and these can be applied either primary, secondary, or variable primary. So covered a bit of ground at this point, so I think it's a good place to stop and see if there's any questions. We have one.
I do have one. Can you use a plate heat exchanger to separate the system?
You can use a plate heat exchanger to separate the system, but from a cost standpoint, you're probably adding unnecessary cost into the system, because the plate heat exchanger is going to probably be more costly than a hydraulic separator. Additionally, I put that plate heat exchanger in there. The low loss header or the closely spaced tees, generally we look at about a 0 psi pressure drop, a 0 foot pressure drop across it. The minute I put a plate heat exchanger in there, now I have to size the pumps for the additional pressure drop across the plate heat exchanger. And also, by putting that plate heat exchanger in there, rather than having one individual system, I now have 2 separate systems. So now I've doubled the amount of makeup water. I need components from 2 makeup water systems. I need 2 expansion tanks, and I need 2 air eliminators. So a lot of times the short answer is yes, you can do it, but there is added cost associated with it with no real benefit if I'm just doing a closed loop system. Okay.
Our next question, with manifolded wall hung boilers, is reverse return piping not needed?
I'm actually that's best answered if I jump back to the picture. So I'm gonna go back to the drawing that was there. Okay, so you'll notice here, this is the manifold systems, and generally when you see and you'll notice here, and also here, there is no reverse return piping. Okay, reverse return piping is paramount if I have a single pump trying to pump through 2, 3, 4 boilers. But here, because each boiler gets a pump, I'm not worried, and as long as I properly size these header pipes, reverse return isn't required. I should see balanced flow through each one of the boilers. But again, the key is the fact that they each receive their own individual pumps. So I see individual pumps here. I see individual pumps here per boiler. But the other key is the manifold system has to be short, and it has to be sized properly for a very low pressure drop to keep it balanced. Okay. Let's see if there's anything else here. Looks like that's it, Miranda.
That is.
All right. So at this point, we'll continue to press forward. So when we look at it so far, so we've kind of talked our way through the different styles of boilers and whether the near boiler piping has to be primary, secondary, or can it be variable primary or primary, secondary. So I think we've kind of worked our way through that. Now it really becomes the next question is, when I look at these systems, and again, I spend a lot of times in the commercial world, what do I do with the off-service boilers, the off-cycle boilers? Because if I have a system with 2, 3, 4 or more boilers, not every boiler is required to fire at all times. So it becomes a matter of what do I do to isolate, or do I isolate the off-service boilers? Do I use isolation valves? Can I get away without isolation valves? If I'm doing primary, secondary, do I want to do individual boiler pumps, or do I want a boiler loop pump in primary, secondary? So this is really our next level of discussion. Okay, so let's start with the no isolation. Okay, this just does show up occasionally. I would say it's a very specialized installation. It's not one that's going to happen that you're going to see a lot of, because of the fact that for this, and we'll go through the discussion of why, I probably would not do this if I was doing more than 2 boilers. And I probably also wouldn't do this if the 2 boilers were there for redundancy. So we tend to see this in systems with 2 boilers, and the 2 boilers are sized for 100% of the load between the pair of them. The other reason that this comes into play is generally in this kind of installation, there is no variable speed pump. So no ECM motor on the pump, no VFD. So I have a fixed speed pump moving a fixed volume of water, regardless of 1 boiler or 2 boilers are operating. Okay. Now we also tend to see this in these boilers here, because of the low pressure drop across the boiler. Now with that fixed speed pump, it really brings in a couple of unique problems when I start to look at low pressure drop boilers. If I have 1 boiler, if I'm only running 50% of load, I would just like to run 1 boiler and isolate 1 boiler. The problem becomes with the fixed speed pump is the fact that I'm tied to this pump curve. So I have this pump curve, and this is let's call this my system curve with both boilers unisolated. So I'll have I'll have the crossover point, and let's call it 38 gallons a minute, okay? Now, ideally, if I was going to isolate the boilers, that 38 gallons per minute, I would love to see it drop down to about 18 to 19 gallons a minute. That way there, I am not overflowing or over pumping the 1 boiler that's in service, okay? The problem becomes, if I have a boiler that only has about 1 foot of head loss across it, when I go from both boilers to a single boiler by isolating, the curve doesn't shift all the way out here, the curve barely budges. So all of a sudden that 38 gallons per minute is probably more, maybe a 30 gallons a minute, but not a whole lot less. And all of a sudden at this 1 boiler operating point, now I start to worry about overflowing or exceeding the maximum flow rate of that boiler, okay? So what happens is it goes in with that fixed speed pump for whatever reason, and then we end up with 2 boilers with no isolation valves. So if this boiler is firing and this boiler is not, I still see flow rate through the 2 of them, okay? The off-service boiler basically becomes a bypass. So return water comes in, flows through the boiler, picks up no heat, and then continues out through, okay? Now my control normally will have a common supply sensor down here, and what that's gonna happen is, because of that common supply sensor driving the temperature, what it's going to end up doing is, because half of the flow is not being heated, the on-service boiler is going to have to run at a higher delta T, twice the delta T, to be able to provide the right water temperature, okay? So if the system was running where this was a 20-degree delta T, across that boiler, I'd probably have a 40-degree delta T to maintain the proper temperature out of the system, okay? Now, that's a theoretical number at maximum fire. Luckily, this building is also these typically are running off of outdoor reset, and outdoor reset works in our favor to get the delta T down. Okay, so back to the BTU formula. So if the system was designed for a 20-degree delta T, if the building is running off of outdoor reset, when the outside temperature is, the delta T from inside to outside is half the design temperature. So I'll work easy numbers. Let's say my inside temperature is supposed to be 70 degrees Fahrenheit. My outside temperature is 0 degrees Fahrenheit. That gives me a 70-degree delta T. On the 0-degree day, I expect both boilers to run. On a 35-degree day, the load on the system is going to be half of the design load. So half the design load, my control should only be running a single boiler. Now, since outdoor temperature drops the water temperature out to the heat emitters output also will be half of what it is on the design day. So if I drop this in half and the gallon per minute is fixed, then the delta T has to be cut in half as well. So on a design day, my delta T here may be 20 degrees, but on that 35-degree day, the delta T here is only 10 degrees. So if I have 10 degrees here, I pick up nothing through the off-service boiler. The on-service boiler is going to run at a 20-degree delta T, much more manageable. So this is what makes this system be able to work under those conditions. It's just what happens is when I run 2 boilers, I get my design delta T across both boilers. But when I'm only running on a single boiler, the delta T has to be high enough to be able to give me the proper common supply temperature going out to the building. Again, this is a specialized case, but I always like to bring it up because it happens. It comes up enough that that's part of the discussion. One other note in here, right here, and parentheses. My preference is primary, secondary piping for this instance. For something like this, if I can talk somebody into it, I will talk them out of doing the non-valved boilers and put them in primary, secondary to be able to better balance the system out. Okay, but we do see systems that do go out like this. Okay, now when I'm doing variable primary, the preference is to add isolation valves to each boiler, and each isolation valves are going to be controlled by the boiler. So when the cascade enables a boiler, the boiler opens up its isolation valve. This way here, I'm only moving water through the boiler that's on service. And in variable primary, because this pump is going to have either a VFD on it or it's going to be ECM, and there's a good chance that it's going to work off of delta P differential pressure. When the valves go open and close, the pump will adjust for the change in the dynamics caused by pulling that boiler out of the circuit, and it will adjust the flow accordingly. Yeah, and again, by doing this, the system delta T, the boiler delta T is the same, and I'm only moving water through the boiler that's required, and the pump will adjust to a lower flow rate to accommodate this. Okay. Now, when I go to primary, secondary, from an isolation standpoint, I have 2 options. I can either do a pump for the boiler loop, or I can do individual boiler pumps. Now, a lot of times we'll see the request come in for an individual boiler pump. Now, in reality, what usually happens is this individual boiler pump actually becomes a pair of pumps because of redundancy. Okay. So I'm going to have a pair of pumps out here in most cases when I have multiple boilers from the aspect of redundancy. So I'm going to add a pump, put an isolation valve at each boiler. Now, because of these isolation valves, I want this pump to be running off of an ECM motor or a VFD so that when boilers are brought in and out of the circuit, the pump will adjust. Okay. And from a design standpoint, so I do this, and then I can set the flow through the boilers based on the needs of the load on the secondary side. Now, a lot of times this is looked upon, and some will say, I like the idea of doing this because of the fact that they're thinking this, single pump and isolation valves versus putting 3 pumps, 1 on each individual boiler. thing to remember is when I do this, from an aspect of redundancy, it's not a single pump. It does have to be 2 pumps. And it's recommended that those 2 pumps are also running off of VFDs or ECM motors. And with the 2 pumps, I also have to be able to have a control that will rotate between the 2 pumps as needed for loading of the system. Okay. Now, my other option is to go with boiler pumps. So here, each boiler gets its own individual pump. The pump is controlled by the boiler control. And so again, just as with the isolation valves, when the boiler is enabled, the enabled boiler starts its pump and flow, and then it will flow water through the boiler itself. Now, the advantage of doing this versus the other install is, first off, the pumps are only sized for the flow rate of the individual boiler. So when I do a single boiler pump, that single boiler pump has to be sized based on the flow rate through all of the boilers. So it tends to be a much bigger pump, okay? Now also, and I'm gonna go in the generic case. In the generic case, these pumps here also can be single speed pumps. Now I don't have to go variable flow on my secondary because my primary is going variable flow. I can go fixed flow here. And by doing fixed flow as a reference point, you look at if I'm doing 2 1 million BTU boilers, these pumps are going to be fixed speed pumps. They're either going to, for example, a UPS 43 100 Grundfos might be the choice, or a Taco 1935 series pump as well could be the pump of choice. So it's a smaller, less costly fixed speed pumps in most cases. Now, I also want to point out here, and this actually came out of a discussion from the previous class, there are boilers out in the market. We provide one of them that internally there are mechanisms to divide up internally to the boiler through isolation valves. So there are boilers on the market that are best served if I'm doing a boiler pump with a pump that has an ECM motor on it or a VFD. But that's something that's very specific. It's not the generic case. And most times the generic case is, a fixed speed pump with something like this. Okay, so this becomes the other option. From an option standpoint and what I see coming and going, I'd say I see more boiler pump systems like you see here than systems that have a secondary, a primary, a boiler loop pump, and then isolation valves on the individual boilers. This tends to be the way I see more projects going. Okay. Now, here's another example showing the boiler pumps. I wanted to throw that out here again. We talked a little bit about this earlier. So if I'm doing wall hung boilers, here's my boiler pumps here off of a manifold. So again, it's primary, secondary, individual pumps, pump size for the specific requirement of the boiler, and it's just for a single boiler. And then the pump starts when the boiler is enabled. Now, next thing we want to touch on is to talk about the air eliminator. Now, when we put drawings together, our drawings, I would say for the most part, tend to show the air separator or the air eliminator on the boiler loop when I'm doing primary, secondary. Occasionally, we'll put it out here on the system loop. A lot of times that's because somebody either sent us a hand drawing that had it out there or somebody requested it. And the question always comes up, which is better? And the answer can be neither one is better or one or the other is better. But I want to point out why the drawings tend to show it here than out there. And it really all comes down to solubility. So here's the solubility table. I pulled this out of Amtrol's Engineering Handbook, something I recommend that everybody has available. If you don't have a copy of it, if you go to, I think, heatinghelp.com, it's in their library. I think they've got that in their library. But this table shows the solubility of water, and solubility is really tied to 2 things, pressure and temperature, okay? And right here, I'm gonna call this baseline solubility. And that baseline solubility, I'm gonna call it right here, okay? So baseline solubility is gonna be based on the pressure at that point, and then if I look at the temperature that's coming out of the boiler. For my example, I'm gonna say the highest water temperature I'll see out of the boiler is 160 degrees. It could be 160, it could be 140, it could be 180. But at 160, and 20 psi. 20 psi was a random number I chose. The solubility is 0.0237, or 2.37% of the system's volume can be dissolved air. That's my solubility, my saturation point, okay? Now, when I start to look at air separation, I want that air separator at the point where this number is going to be the lowest solubility, okay? So if I put this here, solubility is based on temperature and pressure. If I put this here, I know that it's going to be at the highest temperature. And here it's showing tied into the point of no pressure change with the pumps pumping away. I know that it's at a good pressure point. So I'm for a default position based on temperature and pressure, that becomes a great option, okay? If I put it out here, then it becomes variable. There's a lot of variables that play into it. Part of the variables are the flow rate in the boiler loop may not match the flow rate in the system loop. So there may be some mixing. That mixing causes the temperature here to go down, which causes the solubility to become less, okay? So it doesn't become a good option. However, all of these are two-dimensional drawings. They don't show 3D. Let's say I had a 3D drawing and all of this was 25 feet off the floor. All the piping was being run across the roof of the building, the ceiling of the building. All of a sudden, with that change in elevation, the pressure changes and the solubility changes as well. Jump back in here. So that's my point of, that's my baseline point right here. But again, if I said the air separator could be here, if I'm mixing, all of a sudden my 160-degree water can become 150. The solubility goes up. There's air, I don't get all the air that I possibly can out. I can get all the air that I can out here, but when I'm down here, there's air that comes out of solution and then goes back into solution. So I'm not pulling all the air out as possible here based on temperature. But if this was at the top of the building, I may only be at 10 psi versus 20. All of a sudden, the 0.237 becomes a 0.158, or the 2.37% saturation point becomes a 1.58% saturation point. Air comes out of solution right here. So when we start to look at the location for the air separator and how it shows up in the drawings, typically it shows up here because based on limited knowledge, on the boiler side is going to be the best, on the boiler side of the closely spaced T's of the hydraulic separator is going to be the best location from an aspect of pressure and temperature. However, out here, based on pressure, out here may be the best location. So really it's a application by application decision on where it needs to be. But from an aspect of, from a drawing standpoint, we want to show the air separator in here so it goes in the boiler loop because it's the best generic location to work with. And that's why we show it there. Okay. Now, to finish out the system, a couple more things have to come into play. Yeah. We got to make sure that the pump is also properly outfitted. And again, I don't see these always showing up in the drawings, but I like to mention them because they should be there. Suction diffusers and multi-purpose valves. Let's start with the suction diffusers. Okay. Now, for proper pump operation, I should have 10 times the pipe diameter of straight run coming into the inlet of the pump. That allows the flow to turn laminar to reduce the turbulence on the inlet of that pump so it can operate properly. Most of our mechanical rooms are starting to get smaller and smaller, and there may not be the space for this 10 times the diameter. So the suction diffuser goes into the location where it can't be met. So water flow comes in here. It has an open body, and after it comes in the open body, as it approaches the pump, it goes through these straightening veins. So the straightening veins help clear up the turbulence in the water to get it to a more laminar flow as it enters into the pump in those applications where that 10 pipe diameters can't be used. So from a standpoint of the mechanical room, I find a pump. In most cases, I expect to see that suction diffuser on the inlet side. Okay. Now, the other piece of equipment is referred to as a multi-purpose valve. You may hear it referred to as a multifunction valve. You also may hear it referred to as a triple duty valve. And those names come out from the fact that it's not a single-use device. I look at a lot of drawings. The drawings will have an isolation valve and they'll also show a check valve. In the multifunction valve, it operates as a isolation valve. It also operates as a check valve. But the third function is it also operates as a balancing valve. And it does it all here through a single step. So if I bring it all the way down and bring it down tight, it becomes my isolation valve. Okay, you notice it has a spring along here. This shaft and the seat of the valve are not firmly attached to each other. The seat and the shaft can move independently. Okay, so if I back that shaft out, and why am I going to back that shaft out? It's because I'm going to balance the system. So I can use that as a balancing function. I back that shaft out. I have my indicator here, and then I also have my memory indicator in case I use it for isolation. And then I have a pair of ports here that I can put PT plugs in. So I can use this to be able to set the flow from a balancing standpoint to get the proper flow through the pump. And if the end of the shaft is right here, because I balanced it, when the pump starts off, the spring holds the seat in place until the pump pushes, and then the pump will push the seat up until it contacts the stem, and then at that point it's balancing. So that gives me my balancing function and check function in a single seated device. Okay. Now, a lot of times we see the multifunction or the multi-purpose valve not being utilized, and part of the explanation is, well, we don't really need to balance it because of the fact that there's going to be a VFD on the pump. Now, the recommendation is, regardless of whether we're doing a VFD or not, the balancing valve still should be utilized. And I'm going to give you an example of why with a pump curve. So I ran one of our boilers, boiler conditions through TACO's website to size the pump. So I wanted 100 gallons a minute. And based on my calculation, I wanted to, at 10 gallons a minute, the boiler loop was going to have about 5 feet of head loss across it. Now, to give you an idea about what that 5 feet represent, when I ran it through the program said no pumps were available. So the head loss was actually too low for the pump to calculate because the pump shouldn't operate down there. I was able to get it to actually run for me when I brought it all the way up to 7. So here's my operating point here. The blue is my system curve. From an aspect of pump operation, the closer to the center you are here, the better the pump operation is going to be. The higher the efficiency, and from an aspect of operation, the pump and the motor will last longer. So if I don't put a balancing valve in and I sit here, I am compromising the longevity and the performance of my pump. Okay. Now, if I do a VFD, the VFD doesn't change the system curve. The VFD moves the pump curve up and down, expands and contracts it. So I just will continue to move along this line no matter what you do with that VFD. The balancing valve will bring me up to here. So from an aspect of application in near boiler piping, the balancing valve should be there, which means from a standpoint of equipment, we might as well do it through a triple duty valve, a multi-purpose valve. That way there I pick up the check valve, I pick up the balancing valve, and I pick up the isolation valve in a single package. So when I look at a pump in the system, I should see something like this. Here's my suction diffuser because my mechanical room is tight. Here is my multi-purpose valve because I need the check valve, I need the balancing valve, and I need the isolation valve. So that's what I should see around every pump, unless I have the 10 pipe diameters that come in straight on this side here, okay? Now, I will say there is one exception. My one exception is back to the manifold system when I start to do the low mass wall mounted water tube boilers, and you won't find balancing valves in here. Why not? Well, first off, in most cases, the pressure drop across the boiler alone is going to be in that 15 to 16 feet range, which brings it up to where it should be on the pump curve. And from an aspect of packaging, the pump is usually sized properly for the system. So all it needs is a check valve and an isolation valve, and there's no balancing valve in this kind of application. So this does become the exception to the rule when we start to look at the need for the multi-purpose valve. I need a check valve, I need an isolation valve. So back to the beginning. We needed to describe the purpose of components required to complete the boiler installation. The best location for the near boiler piping components. Talked about isolating the off-cycle boilers, and then we talked about the differences between primary only or variable primary and primary secondary piping. With that, thank you for the time, and let's see if we got any more questions. Two questions have come up.
Yes, two questions. From an efficiency standpoint, on a modulating multi-boiler system, when does it make sense to subtract a boiler from operation? Is it when all boilers are operating at minimum burner capacity to ensure most heat exchange surface area?
From an aspect of a multi-boiler system, it's always best to have maximum boilers at minimum input. So to answer your question, the answer is yes. It's best to have that combination. But from an aspect of performance, generally, you know, so if my minimum firing rate is 20%, if I had a 5-to-1 turn down and 20% is my lower side, you know, normally you would say when I can carry that second boiler, the second boiler should come on. Realistically, one of the things we do like to have a little bit of a buffer because we don't want to bring that second boiler on and then have it cycle off, you know, 5-10 minutes later. So it's not where the second boiler comes on at 40%, it's probably going to come on more like 60%. And then the two boilers will drop down to 30%. The opposite also happens when I shed boilers. When I get down close to the point where I can't carry 3 boilers, we drop down to 2. But it's all about it's always about maximum number of boilers at minimum firing rate.
Next question, when, if ever, would a VFD or ECM be used on individual boiler pumps?
Okay, so that's a good question. As far as an individual boiler pump, and here I'm going to actually have to go a little bit on the product specific side of things. So for instance, if I was doing one of our CA3B floor standing boilers, internally those boilers have 2 or 3 modules with isolation valves. So with that boiler, I like to see variable speed on the boiler pump. And what will happen is that variable speed pump is being controlled by the boiler. So when it enables a module, it increases the pump speed, but also when it drops a module, it also will drop the pump speed as well. So the boiler controls the pump, so the pump will be able to best operate under the condition the boiler is operating. Okay. Now, the other one, and this is kind of looking overseas into the European market, which we do over there. If the boiler was modulating the water temperature, I would love to see an ECM pump. But right now we don't have the technology on this side where if the boiler downfires, it drops the flow rate. So we have seen that utilized in the European market. It hasn't made its way over here. But you know, 2 specific cases where it does make sense to have it modulating, the boiler modulating the ECM pump. Yeah.
It looks like that is the last question, Jody.
All right. So again, thank you for attending, and now I'm going to hand it over to Miranda.
Great. Thank you, Jody. Just a few reminders before we close out. As stated, this has been recorded and it will be on the video library within the next 2 weeks or so. So feel free to go rewatch it at that time or tell your colleagues about all of our webinars that are in that video library. We do have a few more webinars coming up this month, including sizing and understanding combi boilers tomorrow and Thursday. And then we're back on Monday and Tuesday with Jody for expansion control. Registration stays open until the start of each session, so feel free to register at any time up until then. If you think of any additional questions, feel free to email me. My email is on the screen right now. We will be putting together a Q&A document that everyone will receive at the end of this week or next week with all of the associated answers. If you wanted to receive the PDH credit, just remember to fill out that survey that everyone will receive via email by the end of the day today. We will be sending out the PDH certificates via email within 2 to 5 business days. With that being said, that does conclude our webinar today. Thank you for attending and have a wonderful day.